When I hit this ball, it's easy to predict exactly where we'll go, at least if I hit it squarely. It hits this rail and rebounds at the same angle it arrived at, then moves on to hit this ball, which, if I'm lucky, should fall in that pocket. Newton's laws of motion help me understand what's behind my game of pool. The same laws of physics tell me that when I drop this billiard ball, it'll fall at the same rate as this chalk. Now imagine a new game where neither the balls nor the rails like to be hit. The balls would try to avoid the cue. The rails might slide back. Other balls would jump or slide to avoid the cue. And imagine that sometimes objects prefer to fall up instead of down. The models we've talked about in economics over the past few programs are much different than the models used by physicists or chemists. That's because economists model the behavior of people, and people respond and change their patterns of behavior in the face of changing conditions. In this segment of Introduction to Economics, we'll discover how economic models are developed and how they're used to help economists and policymakers understand difficult-to-predict behavior. It's the topic of econometrics. Safety devices, such as bike helmets, are designed to reduce accidents, and no doubt they do so. But some riders feel more secure knowing that there is helmet protection and therefore tend to ride more recklessly. A similar example relates to insurance. People who are heavily insured against losses tend to be less careful about protecting their property. These sorts of problems are examples of rational economic behavior that are related to the issues of moral hazard. They highlight the interesting interactions and dynamics that occur when people respond to economic conditions. In the face of this, how do we go about understanding economic decision-making? Well, a good first step is to simplify. We've talked about economic models that are designed to strip away a lot of complexities. In that way, models are very similar to maps. Some maps have an incredible amount of detail, and others are almost schematics. Here's a map of the New York City subway system. It's not designed to accurately show details, but to help you find where to get on and off. It shows only the essential features of the system. A detailed map wouldn't be helpful at all. When you're hiking, you might carry along a topo map, like this one. By presenting details of altitude, you can best judge the terrain and match a route to match your ability and energy. To evaluate the usefulness of a map, we need to always keep in mind the application of that map and not be too quick to criticize when it's used for the wrong purpose. And that's just the way to view an economic model. There are several reasons why we might be interested in economic data and modeling. One is for purposes of prediction or forecasting. In addition to forecasting, modeling can help policymakers assess the best way to affect behavior. A good example relates to demand elasticities for cigarettes. If demand is inelastic, then imposing taxes is a good way to increase tax revenues, but it's not a good way to affect smoking behavior. One of the earliest models in macroeconomics combined theory and data in an original way. It was proposed by William Stanley Jevons in the late 19th century. Jevons collected a massive amount of data on trade cycles. He examined prices of various crops over a 140-year period of time. His analysis revealed a pattern variation in each of the prices that seemed to oscillate with an 11-year cycle. In 1875, he published a paper that argued crop prices were linked to the 11.1-year sunspot cycle. The fact the evidence didn't exactly match didn't deter Jevons. He believed that there were many other variables on the harvest beside the sun. Jevons's theory was international in scope. He didn't believe there was any particular reason why British commerce per se should be affected by the sun, but instead linked it to agricultural output. His data showed an 11-year cycle in famines in India. He He imagined that when agricultural output was low in tropical and subtropical regions, this would push local prices high. Indian peasants then wouldn't have very much money left over to buy British textiles, which would then cause exports to fall. In other words, the sun affected Indian crops, which would cause a commercial blip in British trade. Most of Jevons's colleagues ridiculed the sunspot theory, but the Venus theory was even stranger. In 1914, Henry Moore proposed that economic cycles were driven by weather conditions, which in turn were linked to movements of the planet Venus.
You know, when you've developed this body of theory in economics, which I think is sort of one of economics' strengths relative to other social sciences, we have this great body of theory and predictions of various kinds. You want to sort of test that. You want to sort of figure out if those predictions make any sense. And so you turn to data and to some sort of empirical study. Typically when economists do this, they end up using data that other folks have collected. A lot of it is government data collected by the Commerce Department or the Bureau of Labor Statistics or the Census Bureau, places like that. Unlike other social scientists who are more typically going to collect their own data. We rely on these other sources, and often they're adequate, but often because these data were collected for purposes other than economic research, they don't quite do what we want them to do. For instance, if you look at the census, before 1940, the Census Bureau didn't ask about income at all. It didn't get a precise number. Didn't ask about years of schooling, for instance. These are very important phenomena, very important economic variables, and if we want to study these things over the long term, we're kind of stuck when we use the census. We can't go back before 1940. The census also typically will change the questions that it asks or changes the way that things are coded, the way that answers are categorized from census to census. And so again, if you want to study something over the long term, it's hard to do. Often these things work fine. Often the data is adequate. Sometimes it's not. And so I think increasingly you're seeing economists collect their own data. There are some large long-term surveys. One example would be the panel study of income dynamics, which follows families generation after generation over time. Starts with, I think, 5,000 families and sort of follows their kids as they move out and so forth. Designed to answer questions that economists are interested in. Recently there's been a real spate of new research on the minimum wage. A lot of the evidence in that research is coming out of surveys that economic researchers are just administering themselves. They're just calling up folks who manage Burger Kings and saying, you know, the minimum wage went up so many months ago, how did you adjust your employment? Rather than relying on government data down the line, you know, to try to infer what employers did.
In this class, we'll often make use of graphical models that are based on linear and not trigonometric functions. In your college algebra class, you learned about linear functions of the form y is equal to mx plus b, where x is the independent variable, y is the dependent variable, b is the vertical intercept, and m is the slope. The slope and intercept terms are called parameters. Here's a graph of a line. Notice as the slope parameter m increases, the line becomes steeper. At m equals 0, the line is horizontal. Then we move to negative slopes. At m equals infinity, the line is vertical. The intercept term shifts the line up or down. The slope parameter m tells us how much y will change when x increases by 1 unit. So if the slope is 6, when x goes up by 1 unit, y will increase by 6 units. The dimension of m is measured in units of y per unit of x. The demand curve is often drawn as a straight line with a negative slope. Although we think that the quantity demanded is a function of price, economists flip the independent and dependent variables. So although we'd like to see a demand curve like the quantity demanded is equal to MP plus B, they are normally drawn with Q on the horizontal axis and P on the vertical axis. So B is really the horizontal intercept in economics. The intercept term in our model is what changes when things shift demand. The demand for oranges, for example, changes or shifts due to changes in the price of apples, pears, or grapefruits. The intercept measures autonomous demand, or that part of demand that isn't related to price. Let's look at another example. The supply of money is directly related to the interest rate, which means that banks will supply more money when interest rates are high. As we'll see, the central bank or the Fed in the United States can also affect the money supply by engaging in open market operations.
This shifts the supply of money in an expansionary or contractionary way. In our class, we'll often think about equilibrium as the intersection of two lines. One of the easiest ways to find the intersection is by substitution. If demand is given by the equation QD is equal to AP plus B and QS is equal to CP plus D, then we can solve for the equilibrium price, P sub E, that equates supply and demand by setting our two equations equal to each other. So we have AP plus B is equal to CP plus D, and solving for P by simple algebra. When we substitute this value of P in either equation, we find the equilibrium quantity Q sub E. Linear models are easy to work with and can often nicely approximate nonlinear models, at least over certain ranges of economic variables. For example, here's a graph of a hypothetical relationship between unemployment and inflation. It's certainly not linear, but if we zoom into this range, we see that the relationship is well approximated by the superimposed straight line. A branch of economics that closely relates to data is economic measurement, and statistics is econometrics. For example, econometric methods provide us with estimates of demand and supply elasticities, which are important for prediction and analysis. A fundamental statistical technique that's frequently used to estimate linear models is called ordinary least squares, or regression analysis. It's so widely used that regression, or OLS, is found on most computer spreadsheet programs such as Quattro Pro, Excel, or Lotus 123. So let's see how regression works. We'll begin with some data. We have 12 observations that correspond to 12 families. We have two variables, the family's income and their savings. A scatter plot, which graphs the 12 data points, reveals there's a positive relationship between income and savings. The higher the family's income, the higher the family's savings. Note that the data don't fall exactly on a straight line, but a linear model can be fitted to the data to serve as an approximation. One good method to fit a line is just to stretch a rubber band over the data. This one, for example, seems to have a slope that's a bit too high. Ordinary least squares gives us a line that fits the data in a similar way, but it's based on an exact formula. For this data, here's my eyeball fit, and here's the exact ordinary least squares line. Notice that the fitted lines are very close to the bulk of the data. The difference between the actual values, which are shown in red, and the fitted values, or those on the line in blue, are called the residuals, or the errors. Ordinary least squares fits the line to minimize a function of the residuals. The fitted or predicted values, those are our best guesses about what the dependent variable would be given a value of the independent variable. Using our data, for observation 12, the actual and fitted values are very close. But for observation number 3, the fit is quite a bit below the actual. What this means is that family 3's savings is higher than the model predicts. When the data are highly nonlinear, ordinary least squares techniques have to be adjusted. For example, here's a time series plot of gross domestic product. If we used ordinary least squares on the raw data, the line of best fit would look like this. Clearly, we underpredict early on and later on and overpredict in the middle. A remedy is to straighten out the data, for example, by taking the logarithm of GDP and fitted log GDP on time. As you can see, the transformed data are better approximated by a straight line, and here's the fit.
And now it's time for Chalk Talk with your host, Miss Sarah.
Okay, what I've drawn on the board is a relationship between income and education for a group of people, and each different dot represents a different person. And as you can see, there's a positive relationship. As education increases, income increases. So what we want to do is find the ordinary least squares, which is a line that goes through these dots that's the best estimate of these dots. And it's a line that minimizes the sum of the squared residuals. The residuals being the distance between the actual line and the dot. So if we put a line down here, while it runs through 3 points, the residuals are quite large for these other ones. So a line here, while it may not run through only any more than 1 point, might be the best estimate of that line because it minimizes the residuals. So we draw a line like that, and that would be our estimate of the relationship between education and income.
When we look at the price quantity data, we have to be a bit careful about how we interpret it, and theory can help us a lot. For example, here's a plot of annual corn data showing prices and quantities for 15 years. We've plotted the data with price on the vertical axis and quantity on the horizontal axis. Viewing the data, we're inclined to think we see a demand for corn with a fitted line that looks like this. Now, if this is the demand curve, where's the supply curve? As we've seen before, both supply and demand determine observed price. So let's look at the data point corresponding to 1990, highlighted here. This observation could result from many demand and supply curves, each intersecting at this point. For example, we've pictured a new demand curve, D1, and supply curve, S1. Notice the slope of the real demand curve is much more elastic than the original demand curve we saw earlier when we first plotted the data.
The data don't exactly speak for themselves. You'd like that to be the case. I mean, you'd like it to be the case that if we all look at the same numbers, we're going to come out in the same place. We're going to agree on what the answer is. But that's not the case. I mean, part of the problem that economists and other social scientists face is that we're not doing lab work here. If a biologist wants to know whether a certain chemical affects the growth of bacteria, then she might develop two bacterial cultures under identical conditions and just administer the chemical in question to one of them. Any differences that result are going to be due to that one difference. It's a controlled experiment. And we can't do that. To stick with this minimum wage question, for example, if the minimum wage rises at some point in time, employers are going to adjust to that over time, probably. But during the time when employers are adjusting, lots of other stuff might happen. You might be interested in the effect of the minimum wage on teenage unemployment. Well, maybe the labor supply behavior of teenagers will change over time, or simply the number of young folks around will change. Labor demand in industries that employ a lot of teenagers may change. Trade policy may change and may have an effect on that. The economy as a whole may grow stronger or weaker. So all these things are going to affect the unemployment rate. They're changing at the same time the minimum wage is changing, and you can't control them. So what we try to do, what economists typically try to do, is come up with ways of estimating the relationships that we're interested in that are going to look like controlled experiments. And so you see these references to regression techniques, and quite typically linear regression, which might try to get at the correlation between the variable you're interested in, teenage unemployment, and the cause that you're interested in, the change in the minimum wage. It'll check the correlation of the outcome you care about with all of the things that you think will matter. And the estimates that it produces should tell you something about how the minimum wage affects teenage unemployment, holding all those other things fixed, as if you'd done a controlled experiment. That's the idea. It doesn't work exactly that way. There's always criticisms that can be leveled.
Another common problem in econometrics relates to out-of-sample forecasting. Here's a picture of the problem. We collect data on the relationship between X and Y. It appears that a linear model is a pretty good way to describe the fit, so we go ahead and fit a line, feeling fairly comfortable with the model. What happens, though, if we're given a value of X that's not close to the data that we use to fit the model? We can still use the regression estimate to predict Y, but if the fundamental relationship is not linear, our guess might not be very good. Out-of-sample forecasting is a difficult challenge, and econometricians are constantly devising new methods to help overcome statistical obstacles. One of the most common mistakes we make when working with data relates to our interpretation of patterns. If you flip a coin 20 times and make a mark of a +1 if the coin lands on its head and a -1 if it lands on its tail, you'll usually be able to detect a clear cycle in the data, a pattern that's not unlike slices of stock market data. With the coin, it's easy to remind ourselves the data are in fact random. It's in our brain that wants to make sense of it. When thinking about investing, it's much more difficult to believe stock prices aren't driven by unknown forces. Without theory, it's often easy to confuse correlation with causation. For example, people drive more slowly when it rains. Here are some hypothetical data matching average speed and accidents. The plot reveals that accidents tend to fall with increasing speed. Just looking at this data might suggest that policymakers increase the speed limit to reduce accident rates. What we fail to consider, though, is that in this particular case, rain is the culprit for driving accidents. This same problem, omitting a relevant variable, leads to funny sorts of conclusion. Fair-skinned people tend to be susceptible to sunburn, but having fair skin doesn't cause sunburn. Both characteristics are, in fact, related to a genetic inheritance, something that may be difficult to measure. Statistical analysis and regression are important tools that are widely used in modeling, but simpler tools can be just as important, and those are visual tools. Graphs can be more convincing than analytical presentations, but we have to be cautious because things often aren't what they seem. Sometimes, just the way you see the data can influence decisions in important ways. For example, here's a time series plot showing the rate of unemployment in the U.S. economy from 1950 to 1990. Let's take exactly the same data and change the scale of the axis. The top picture is one of stability, while the bottom graph shows apparently wild fluctuations. Now, the only difference is the scale of the vertical axis. The aspect ratio of a graph is the ratio of the vertical dimension of the graph to the horizontal dimension. Here's a picture of annual rainfall in New York City. We've drawn the graph so it's tall and it looks like there's no pattern in rainfall. But now let's change the aspect ratio to a graph that's short and squatty. What we find is a clear oscillating pattern. So just by changing the aspect ratio of the graph, we were able to see something in the data that wasn't apparent before. When you see graphs, you should look closely at scale and aspect. And where generating your own graphs, you can experiment with the plots you make and see the various effects of changes in scale or aspect. So far, we've thought about two-dimensional visualization, such as scatter plots and time series plots. But if we can add more dimensions to our graphs, we can picture even more. Computer programs are now good at generating three-dimensional graphics or plotting surfaces which can be rotated easily. Here's a picture of the rainfall, speed, accident data we talked about a bit earlier. Let's rotate the data cloud a bit. In doing so, we see the accident speed link. The higher the speed, the lower the accident rate. But next, we see the speed rainfall link. And finally, we rotate to find the link between accidents and rainfall, which leads us to a more plausible explanation for accidents on the highway. They happen more frequently when the pavement is slippery. When we go beyond three dimensions, it's difficult to visualize relationships. That's why analytic models become so important. Econometric models of the United States are used widely. Some models have parameters that appear in thousands of equations. These models are used to help businesses and government policymakers understand how economic variables affect our lives. Our simple model of supply and demand is the basis for these immense systems. In microeconomics, we move to explore the model in more detail, to figure out exactly what behavior is behind the demand and the supply curves by looking at economic decision makers, consumers, and firms. In macro, we move in the other direction by aggregating across sectors in the economy in order to understand the overall economic forces that affect unemployment, inflation, and economic growth. Now you know where we're heading, so let's explore the theory of demand and supply in depth and focus a microscope on the behavior of individuals in our economy.
As man seeks an understanding of the still smaller world beyond the microscope, probing the endless form and variety of living things, scientists come ever closer to an understanding of the wondrous process by which they function.